Okay, good afternoon. Hello. So today's the last lecture, and we devoted to review. Please don't forget that the final is tomorrow. Okay, and the tutoring center is open in the morning, so if you have some last-minute questions, please ask them. Don't forget to bring your ID. If you forget your ID or your picture is not clear on the ID, you have problems. Especially because they will call you out and talk to you, and you lose minutes, you lose time. Okay, so please don't forget your documents. So this is the third time we're doing review in this class. We did one for the first midterm, the second one for the second midterm, and now the third time. So I want to emphasize the topics that we studied last, because these are the freshest in our brains, and we don't. We need more. We need to put the most thought into those, okay? And then I'll touch on the other parts of the class. Of course, the final is comprehensive, so it will start with the definition of integral, fundamental theorem of calculus, Riemann sums, stuff like this. We'll be calculating the area under the curve, the average value of a function, the volumes, the washers, stuff like this. And then we'll go to techniques of integration. All of this is covered. But now, today, let's start with techniques pertaining to series and their convergence. So convergence, sorry. So I'll give you a few examples. So for example, whether this series converges or not, you can see that it looks like a function, and this function is something that we can integrate. So we consider f of x that's given by this expression, right? And we want to evaluate the integral of f of x dx. If that converges, then our series will converge too. So we're looking at an integral x plus 5, okay? And this is an improper integral, so we have to remember everything about those, right? So how do we do an improper integral? This is type 1 improper integral when it's continuous in this domain, but the domain goes to infinity. So we set up a variable t, which is the upper limit of integration, and let that go to infinity. So once we wrote that, we can stop here and just calculate the proper integral, right? And then take the limit. What is the appropriate method for this simple integral? Substitution, right? We said that u is x plus 5. And when x is 1, u is 6. So we t plus 5. Okay. So we have du over times u minus 1/2 du, okay? And when we evaluate the antiderivative, it gives me square root of u. So we have this expression, right? So finally we have to evaluate the limit as t goes to infinity of this. As is easy to see, it diverges, right? The limit is infinity. Therefore, the series diverges by the integral test. Okay. Please remember the names of the tests and put them on your final to tell the grader that you know what you're doing. Even if you make a mistake, you tell them that, okay, I used this test. The next example, let's look at this one. If you see a factorial, then question?
Can we show on the final that it's positive, continuous, and decreasing for that size?
Yes, well, I'm not sure about the way the grade. Perhaps even if you don't do this, you can still get the full score, but I'm not 100% sure. So if you know how to do this, do this. Okay. Okay. So when you see a factorial like this, it's a good idea to apply the ratio test. So we have to look at the limit as n goes to infinity of a n plus 1 over a n. Okay. So we have to become really good at operating with factorials, right? What is n factorial divided by n plus 1 factorial? It's 1 over n plus 1, right? How about powers? 100 to the power n plus 1 divided by 100 to the n. That's just give me 100, right? And of course, this goes to 0, okay, as n goes to infinity. As long as it goes to something that's less than 1, we're good. Okay, so this converges. The next one, also a typical one. Okay. So this integral has minus 1 to the n, so it's alternating series. So let's test that. So alternating series test. There are two conditions that need to be satisfied. Vn plus 1 is less than Vn, and Vn go to 0, right? So let's check. So you can see that Vn is not an easy expression in this case. Sometimes you can just tell that it, but here we have this combination. So the best thing to do, and we have to see whether this decreases or not. We want it to decrease. So we are going to use the power of continuous analysis. We are going to look at the function f of x that's just like this. Because with functions, we can take derivatives. Okay, and then we don't have to worry about anything. If derivative is negative, we're good. So calculate f prime. Okay. I don't think there's a 2 here. Okay. I don't seem to get what I have in my notes, so 1 second. Did I make a mistake? Okay, I'm not happy because it should decrease. And I'm getting a positive derivative. Oh, there's a 2 here. Here. There's a 2. Okay, so for large enough x, if x is greater than 5/2, f prime is less than 0. Okay? So my mistake was when I was taking the derivative here, I forgot to differentiate 2x plus 5 separately to get this 2. Okay? Nobody caught my mistake. That's not very good. Okay, so the derivative is negative. And this means that the first condition is satisfied. Now we want to make sure that the limit is 0. So what happens to square root of n? What's the limit of square root of n to n plus 5? So the general method is to divide by square root of n, right? So I have divide by n. And that goes to 0. Okay? So the second condition is also satisfied. And then we can conclude that the series converges by the alternating series test. Okay? Questions? Okay. Here's another one. Let's look at this one. Okay. So what is the method here? In principle, I want to use a comparison test. What do I want to compare it with? So my given series has terms 1 over n log n plus 3. And I want to compare it with something that looks simpler, like this, n log n, right? And then maybe I can say something about this one. So first of all, let's see if the test will hold. So I'm going to use the limiting version of this. The ratio an over bn should approach some number which is not 0 or neither 0 nor infinity. Okay, as long as it's some finite number, I'm good. So I have n log n plus 3, and here I have n log n. Okay. So limit. So I have log n plus 3. How do you calculate this limit? Where does it go to? Well, there is one thing that you can do here. You can write n plus 3 as n1 plus 3 over n. Okay? And then the log of n plus 3 becomes the log of n 1 minus 3 over n. I'm sorry, plus, like this. So we have a log of a product. Okay? So I have log n, and I have log of n 1 plus 3 over n. What happens to a log of a product? It falls into a sum, right, of the two logs. So we have log n here, And here we have log n plus log 1 plus 3 over n. So now it's easy. Because when n goes to infinity, 3 over n disappears. Here we have log of 1, which is 0. And we have log n over log n, which is 1. So we can apply the comparison test. Now the question is, what does this series do? The one we're comparing with. It's not necessarily the easiest of them, right? Let's look at its behavior. So what happens to Bn, which is 1 over n log n. Okay, so now we can use the integral test. And we can, starting from some constant, evaluate the integral of this function. Okay. So this is the method I would use here. This looks like this function. So where do I start with? Here's a good question. I could start with 0, not a good idea, because it's discontinuous. I could start with 1, also not a good idea, because logs goes to 0. So let's start with some finite constant which is greater than 1. I don't care what it is. If a is greater than 1, then it's continuous there. I don't have to worry about it. And the test works for any finite bottom limit, as long as the top limit is infinity. Okay? So we have to consider this quantity. What's the method of evaluating this integral? So now we have an integral from a to t, 1 over x log x dx. Then t will go to infinity. What's the method? U substitution. So we have u equals log x, du is 1 over x dx. So we have log a log t du over u. So we have log t minus log a. I missed one step. If you like, I'll fill it in. Whoop. Log u evaluated at log a log t. So it's a log of log t. So it's log t minus log a. That one. Questions? What does this do as t goes to infinity? Goes to infinity, right? Because log grows to infinity and its own log grows. It grows very slowly, okay, but it will grow infinity. So the series diverges. So I use two tests here. One is a comparison test to bring it to this form, and then I use the integral test. Okay. Question?
Can you just do the integral test at the beginning too?
I could do that. Then I would have to evaluate this integral. So in my mind, it was easier for me to first get rid of this 3 and then calculate this integral. If you want to calculate this integral, you can do that too. But for me, the two-step kind of seems a little bit conceptually better. I don't know. OK. So let me shift gears a little bit, because I want to cover one topic that was not covered in the last midterm. OK. One second. So so here, the topic that we didn't include in the midterm was calculating the arc length. Okay. So please pay attention. So arc length. So I want you to do some examples at home when you prepare, just to make sure that you remember the formula and you know what you're doing. Okay, arc length is something that we didn't really do. So calculate the arc length of the curve y is given by log cos x for x between 0 and pi over 4, right? So we always do these problems in the same way. First, we start by calculating dy dx, okay? So the formula is 1 plus dy dx squared dx, right? So that's what we're aiming at. So first we calculate the derivative. It's a composite function. So we have minus sign here. So that gives me minus tangent x. Okay. Next, when we put it under the square root, we have a nice nice identity to use. This is secant squared, right? So this is just secant x. Therefore, the arc length L is given by an integral from 0 to pi over 4 secant x dx. Okay, questions? So what's the integral of secant? In this problem, it's given, right? This is log of secant x plus tangent x from 0 to pi over 4. So we have log of square root of 2, because cosine of pi over 4 is 1 over square root of 2, so secant is square root of 2, and tangent is equal to 1. Okay, minus log, what's the secant of 0? That will be 1, and the tangent of 0 is 0. So log of 1. So the whole thing is log of 1 plus square root of 2. Questions? So this, from here to here, is an integral that you may or may not remember. It's very difficult to calculate, and here it's given as a hint. I don't think you should actually remember it. Okay. Let me find another arc length for you. I have another arc length. So arc length for the function y, 1 plus 6 x 3/2 between 0 and 1. Okay, let's do this one. dy dx, we calculate the derivative. So I have 6 times 3/2 x 1/2. So I have an integral from 0 to 1 of square root of 1. So dy dx squared becomes what? This is 9, so it's 81x. Okay, 1 plus 81x dx. This is the integral that we end up evaluating. So we can do a u substitution. 81x plus 1. So du is 81 dx. When x is 0, u is 1, x is 1, u is 82. So it's an integral from 1 to 82 of square root of u du over 81. Okay, not very pretty. So I have square root of u 3/2 - So this is the answer. Okay. So I give you 2 examples of this because we didn't have that on the midterm. Any questions about arc length? Okay. So now, Taylor series and Maclaurin series. I'm going to give you a tricky one. Yes, question?
Yeah, 3 over 2, when you integrate, where is u? Don't get divided by the negative. Multiply by 2/3.
When you integrate square root of u, you don't divide by 2/3, or multiply by 2/3.
Oh, I forgot. Yeah, 3. Thank you. So let me give you a Maclaurin series example. Of this function, okay? So there are 2 ways of doing it. The long and horrible one and the short one, okay? The long way would be, I have to, so in either way, you have to remember that Maclaurin series looks like this. Okay? This is the general, you have to remember this, okay? Now, in order to do this problem the long way, we have to evaluate all of these. So we have to write down the function, its first derivative, the second derivative, third derivative, and so on. And on this, in the second column, we evaluate all of these derivatives at 0. Okay? We can do that, but we don't want to do this for the following reason. You can, we can say that, recall that there is a very nice function, okay? There is a very nice function, sorry, e to the x, whose Maclaurin series we should know, okay? Because it's very, very simple, like this. Remember, we derived this in class. This is the easiest and simplest Maclaurin series of all, the exponent. Why? Because for the exponent, all the derivatives are equal to e to the x, and all the derivatives evaluated at 0 are equal to e to the 0, which is 1. So we just have x to the n divided by n factorial. Okay, so this is the easiest one. Now, how can we go from here to this? First, we can say that, what is e to the minus x? From here, without thinking. We replace x with minus x. So we have minus x to the n factorial. And in fact, you can rewrite it nicer. Sorry, starting from 0. We can have minus 1 to the n, right? So it has this nice alternating series shape. Okay, so I have e to the minus x. How do you go from here to here? Multiply by x squared. Look at this. So I incorporated x into the n, right? So now this is the answer. What is the radius of convergence for this? We remember that the radius of convergence for this nicest Maclaurin function is infinity. Okay? Therefore, because of all these operations, it doesn't change. And we can say that r is equal to infinity here too. Okay? For the same reason that r is equal to infinity here. And we calculate, it's a known fact, we calculated this in class. Okay. Very good questions. Question?
So
So no matter what you do, then at the end the radius is the same.
So if you differentiate the series, integrate the series, multiply it by a number, interchange x with minus x, then it doesn't change. Okay? If you multiply x by a different number, then it will change. Unless it's infinity, it will remain infinity. But if, for instance, the radius of convergence was equal to 1, and you replace, for a certain series, and then you replace x with 2x, now 2x has to be smaller than 1. So the radius becomes 1/2. Okay? So if before x was less than 1, and now you replace it with 2x, then x now is less than 1/2. So this is your new radius of convergence. But this doesn't pertain to this example. Okay.
I was also wondering, should we memorize like the whole table?
Oh.
Because are we just going to get examples like this? I don't know.
This for sure I would memorize. I'm not sure about sine and cosine. We've only been teaching this a few times. I don't know. I don't know. So memorize this, and it's probably okay. Yep.
Would this only apply to this problem, or could you do it with different ones? Say if it was instead of x squared, it was sine of x e to the negative x.
Oh, no, that would not apply, because in this case, you have sine here. So when you multiply through by sine, it stops being a power series right here. So you would have sine x here. You multiply through, and it doesn't look like a power series anymore.
Okay.
So if you have some complicated function, like sine e to the minus x, there are a few ways of doing it. One is just the straightforward way. You calculate all the derivatives, try to find a pattern, calculate, and then evaluate all the derivatives at 0. Okay. Okay. Let's see what else. Let me do something completely different. Okay. So how about this one? Evaluate d dx evaluate at x equals 3. Okay? So first we have to calculate the derivative. This is the fundamental theorem of calculus part 1. When we evaluate the derivative of this, we just get d dx of this thing is equal to the integrand evaluated at x. Okay? Therefore, when we evaluate this x equals 3, we have square root of sine of 24. Questions? Question?
So the lower limit doesn't mean anything?
Okay. So fundamental theorem of calculus talks about the function g of x that looks like this. Okay? When you evaluate the derivative of this, the answer is very simple. It's just f of x. Okay? Now, and this case appears here, so this doesn't matter. You simply take the integrand and evaluate it at x. Now, the lower limit will matter if it's a function of x. So let's consider a more complicated example. How about g of x is x squared to I don't know, cosine x. f of t dt. Okay? So what's the derivative of that? So now both limits of an equation are a function of x. And it's a little bit more complicated because it becomes a composite function. So first we differentiate ddx cos x, okay, times f of cos x minus, because it's a lower limit, ddx x squared times f of x squared. So we can rewrite it as minus sine x, f of cos x, minus 2x f of x squared. Okay? So the lower limit doesn't matter if it's a constant. If it's not a constant, it matters very much. It comes here with the minus sign, and we'll have to differentiate it. If the upper limit is not a constant, we also have to differentiate it. More questions?
If it's like a constant at the top and then x on the bottom, can we use this rule?
You flip it. Yes, of course. Well, if it's an integral from x to b, okay, f of t dt, the easiest way is to rewrite it as minus integral from b to x. Right? You can flip the limits, and then you apply the fundamental theorem of calculus in its pure form, but you'll have the minus sign. Okay. Okay. How about evaluating an integral or two? Oh wait, I had a very good problem with improper integrals. Let me find that. This one. So before I actually do this problem, let me do a really simple problem for you, so you know what I'm talking about. An integral from 0 to 5, okay? In one of the midterms, I think the second one, a lot of people said that this is equal to the log of x minus 3 evaluated. So this is not equal to log of x minus 3 absolute value. Evaluated at 0 and 5. So this is log of 2 minus log of 3. This is wrong, okay? Because what we are overlooking is the fact that this is a discontinuous function, and the discontinuity lies between 0 and 5. At 3, the function does something bad, okay? It does this, okay? So we cannot simply blindly do the antiderivative. It's not a continuous function. It's an improper integral of the second kind. Please don't ignore this fact. It's very easy to overlook. But if you look at the denominator, it turns into 0 inside the limit of integration. It means that we have a problem, and we have to look at that. So the way to do it, we have to say that this integral is actually a sum of two integrals. One goes up to 3. 3 is the problem point, right? That's where the function does its jump. And then from 3 to 5. And now you can take either of them, okay, and start evaluating it. So this integral is equal to the limit as t goes to 3 on the left of this. Okay, we replace the problem limit. This is the problem limit. This is where the function experiences a discontinuity. We replace it with t, and later we take t all the way to 3, right? But now we calculate this. So this becomes the limit of this log of t minus 3 minus log of 3. What's the limit of that? When t approaches 3, this guy is a log of 0. And of course, is infinite. It's actual minus infinity. Therefore, the integral diverges. And we don't even have to bother with the second half. Okay, this is enough. If it did converge and we found the limit, then we would have to evaluate the second one too. Right? If one of them diverges, you're done. You say the integral diverges. It's an improper integral. It looks completely innocent, but it's hiding a singularity, and it gives it an infinite value. Okay? So now I'll give you a more sophisticated one of the same type, of a similar type. Any questions about this? Look at this one. So this integral, if you just look at it, potentially could be an improper integral in two senses. One, the limit of integration goes to infinity. Two, this guy can be 0 inside the limit of integration. So let's see what this is equal to. If you solve this quadratic equation, you find that this is equal to z plus 2, z plus 1. Okay? So you can rewrite this guy . So now tell me, do we have to worry about the discontinuities of the integrand? No, because they luckily are outside of our limit of integration, right? If it was like z minus 2, then yes, we would have to, if this was z minus 2, we would have to integrate from 0 to 2, and then from 2 to some constant, from that constant to infinity. Okay, that would be the procedure. But now it turns out that the singularity are not a problem, and we're dealing with a purely first type of an improper integral. So how do we take this integral? How do we evaluate this integral? By parts, right? By parts. Partial fractions. So to make the long story short, we can say this. This is equal to the limit as t goes to infinity. We have dz. No, we have a sum of two fractions. This step I'm skipping is finding a and b. A is minus 1, b is 1. It's easy. Okay? So we have the limit as t goes to infinity of the log of z plus 1 minus the log of z plus 2. Or we can even say that this is the log of z plus 1 over z plus 2. What's the limit? Oh, I'm sorry. This is because I skipped a step. Okay, let me just do it correctly. So I have this is correct from 0 to t, okay? And this is log of z plus 1, z plus 2 from 0 to t, right? So I have a log of t plus 1 over t plus 2 minus log of 1/2. What's the limit of this? This quantity under the logarithm tends to 1. Therefore, the log of 1 is 0. And I have minus log 1/2. So this is the answer. Okay. Questions? Okay. I had another one that I want to show you. This one. find the sum of the series. Okay, so I'll give you this one. It's completely unclear how to actually find the limit. You can prove it converges. That's easy. You can use the comparison test with 1 over n squared, for instance, but which is a p sequence. But how do you calculate the sum? So here you do it by partial fractions, just like here. Okay, it's very strange, but you can present this as a over n plus b over n plus 3, just like with the x's, right? And you can find a and b. And the answer is like this. They are both, one of them is 1/3 and the other one is minus 1/3. So this is equal to this. So this whole thing is equal to this, 1 over n minus 1 over n plus 3. And you ask you, how does this help? It helps very much for the following reason. So we're going to start writing these term by term, skipping the sigma notation. So what's the first term? It's 1 over 1 minus 1 over 4. That is when n equals 1. When n equals 2, I have 1 over 2 minus 1 over 5. When n equals, so this is n equals 1, n equals 2, n equals 3 gives me 1 over 3 minus 1 over 6. And I continue, plus 1 over 4 minus 1 over 7, plus 1 over 5 minus 1 over 8, plus 1 over 6 minus 1 over 9. So 4, 5, 6, and so on. And what do we observe? So many of them cancel. Question is how many, right? So this cancels with this. 1 over 5 finds its partner. 1 over 6 is cancelled. When n is 7, this one will also find cancellation. So all of them will cancel. Which ones will not cancel? Yes, this one, and that one. So the answer is 1 plus 1/3 plus 1/6 times 1/3. And that's equal to 11/18. Okay, very clever method. So this is called the telescopic sum. When you, zoom this telescope, you can collapse a telescope, and only a finite number of terms is left. Question?
What happened to the n term?
So this was kind of a shortcut. I said that as you go to infinity, they all cancel. You can also calculate partial sums. So you limit this to n capital terms, and then you can calculate the limit as n goes to infinity, and you'll see that it gives you the same answer. Question? Well, in general, it depends on the difference between this. See, here they differ by 3. That's why the first 3 didn't find a partner.
Okay.
If it was like n plus 10, then the first 10 would stay. Question? Oh, yes. That's correct, but the final answer is correct. Thank you. Question?
Why do you multiply by 1/3?
Oh, because when I calculated A and B, A was equal to 1/3 and B was equal to minus 1/3. So 1/3 came out. So it's been a pleasure to teach you, and best of luck tomorrow at the final. Thank you.